Daniel Catan. And so I'm going to mostly talk about the incompressible Euler equations today, but pretty much for most of what I say, what's true about incompressible will also be true for the compressible model as well. So let me just begin by writing down the equations. So these are familiar to most everyone in the audience. So here are the Euler equations in the incompressible form. And the first part that I want to discuss, in fact, it'll probably take most of the talk, is the so-called one-phase problem. So here, there's initial data that's specified in the form of some initial domain omega 0 and some initial velocity u0. And then this equation is set on a moving domain. So there's some family of transformations which map this into the moving domain omega of t and u of t. And I'm going to call the boundary gamma of t. So what I mean by this is that there's a fluid here, and then there's nothing, no model on the outside. You can think of it as vacuum. So that's one scenario, and in this scenario, this equation is set in omega of t, and one specifies that the pressure vanishes on the boundary. And then one has to give the dynamics of the boundary, and in this case, the boundary is moving with the fluid, and I'm going to sort of symbolically write that the velocity or the normal velocity of this boundary is u dotted with n. And then in addition, you specify the initial states of the system. So this is the so-called one-phase model. And as I'll discuss in a moment, this is not always well posed. In order for it to be well posed, there's a certain Rayleigh-Taylor condition that has to be satisfied at time 0. And because of this, you can view this boundary also as a surface of discontinuity, in this case for the pressure gradient. And in the compressible model, you can really view this as a real characteristic degeneracy where you have vacuum here and two wave families are meeting on this interface. And then there's a two-phase model. And by the way, here I'm drawing this geometry. You can also view this geometry more in terms of what I'm going to talk about, a perturbation of like the ocean when the wind is blowing. So this might be omega 0 and then omega of t, it doesn't really matter. And then in the two-phase model, you have equations in each phase. So here you can sort of think of this scenario here. Here's the interface gamma of t, and here's omega plus of t, and here's omega minus of t. And you have these equations holding in each phase, so ut plus minus, plus the advection term, plus the gradient term, and then, so each one of these equations holds an omega plus and an omega minus, and then there's a jump. So here the normal component of velocity is 0, but the tangential component of velocity jumps. So this is like a contact discontinuity or a vortex sheet. And to make this well posed, one says that the jump of the pressure is some surface tension parameter times the mean curvature of the interface. And again, as Danny said, I'm drawing this as a two-dimensional picture, but I'm really thinking about everything being in 3D or 2D, but there's no limitation to the dimension here.
And you keep the same dynamics for the interface.
I'm sorry? Right, the same dynamics for the interface, that's right. So again, it's moving with the fluid. So there's a simplification to these problems. In particular, let me sort of focus on the one-phase problem for a moment. So this is known as the water waves equations. And it's not too difficult. Basically, if you take if you let omega denote the curl of the velocity field u, this is called vorticity, and you take the curl of this equation, you see that the vorticity is transported. And so if it's 0 at time 0, it remains 0 for as long as one has a nice solution. And so if you start with an initial velocity field which is 0, this implies that omega of t, which is curl u of t, is also 0, as long as the solution exists. And then if you sort of think in terms of a perturbation off of, say, a flat interface or something, and you think of this as the height, the sine height function, h of x comma t, together with the fact that u is divergence free, u has a velocity potential, and phi and h form, satisfy some quasi-linear, very non-local hyperbolic system, which I'll just sort of write as something which is a function of phi and phi x and h hx, and it involves the Dirichlet-to-Neumann operator. And this is a nice simplification in the sense that the velocity field is just simple potential flow, but everything reduces to the motion of the interface. And I'm introducing this just from the point of view that I want to place the results I want to talk about today sort of as being complementary to some of the recent global existence results that have been obtained for this equation. So let me just, I'm going to skip most of the history on these results because it would take me the rest of the talk to do any justice to it. But just a very brief history. So this, let me first introduce the Rayleigh-Taylor condition, just so I can talk about the history. Is that right? So this is sometimes called the Rayleigh-Taylor or the Rayleigh-Taylor sign condition. And if one doesn't want to study the problem in this simplified, what's called irrotational form, then you need to specify some condition on the initial pressure. This condition is the following. So in this picture here, let me denote capital N to be the unit normal at time 0 and little n of t to be the unit normal at time t. The Rayleigh-Taylor sign condition says that if you have dp0 dn being greater than or equal to some lambda, which is strictly positive, on the initial boundary gamma, this is sort of a necessary condition for well-posedness, which I'll talk about in a moment. The way one computes this pressure is that you are given an initial velocity field u0, and you solve an elliptic equation, minus Laplacian p0 is equal to the trace of gradient u0 contracted with itself in the initial domain omega together with a boundary condition, p0 vanishes on the initial boundary gamma. And then you have to pick a velocity field such that this condition is satisfied, and if it's not, you get ill-posedness. And there have been a number of papers starting with Saiji Wu's results for the water waves equation, culminating in a series of works in sort of the mid to late 2000, between 2000 and 2010. And the one theorem that I want to talk about, that I'm going to use for the remainder of the talk, is a theorem with Daniel Coutand in 2007. This is our version of the well-posedness result, which I'll elaborate further shortly. But this is, as far as I know, this result is the only one that allows arbitrary initial geometries.
So now it is well posed. So what is two phase, one of this problem?
So for now, I'm going to talk about this problem, but we also have well-posedness for this problem. Both of these problems are well-posed. The difference is that, so in this paper here, let me just say that if the Rayleigh-Taylor condition holds, then you have local in time well-posedness for arbitrary domains. Most of the results in this business are for perturbations of half spaces, or there's some constraints on the geometry, but for the result I want to talk about today, you really need to be able to solve this on an arbitrary geometry.
So it's where Laplacian of P0 is equal to something in omega 0.
Did I say omega 0 there? Yeah. Let me put omega 0. Sometimes I forget the subscript 0, so thank you. So this should be 0 too. So I'll elaborate on this, but there have been a number of results by many people, but this is the one that I wish to use. So the theorem that I want to talk about today, there's two theorems I want to sort of discuss today. So this is regarding interface singularities. So these are sometimes called splash or splat singularities. I'm just going to draw a picture. So the picture is the following. So you start with a smooth initial state. So you're given some initial omega 0 and u 0. So this might be time t equals 0. And then, again, I'll make this a little bit more precise in a moment, but I just want to draw a picture. The point is that there exists some time capital T where the surface does something like this. This hypersurface will turn over and self-intersect at, say, a point, x0. So here's the domain omega of t. So this is under Euler evolution. And this is called a splash singularity when it intersects at a point, or it could intersect at a hypersurface, and that's called a splat singularity. So it could. So this could be, let's say, gamma s, which is a hypersurface, and this is called a splat. And this is for the one-phase model. So there were sort of a couple of us thinking about this at the same time. There's two theorems on this, which are pretty similar. We were thinking about this because we wanted to do something with a vacuum problem that required this sort of self-intersection. And simultaneously, Diego Cordova and his group were doing these numerical simulations on water waves. And what they were seeing was that in this water wave problem, you actually had this kind of interface singularity forming while you had locally smooth surfaces from each side. So in other words, in this one-phase problem, without any sort of regularity loss, you had these two smooth surfaces that were colliding. So Diego started talking with Charlie Pfefferman about this, and Pfefferman had this idea to use analyticity in these conformal transformations to establish this result analytically. And so there's sort of two very similar theorems. So there's a theorem by Castro and Cordova and Pfefferman. Acevedo and Gomez. And what they prove here is the finite time splash singularity for the 2D water wave problem. So their method relies on these interesting conformal transformations and the use of some pretty sophisticated analyticity machinery. And simultaneously, we have this result with Catan, which says basically that, again, it's a finite time splash singularity, but we can do this in any dimension. And it's not just limited to, let me call this theorem 1, let me call this theorem 0.
Is this existence as finite time singularity? Is that?
Yeah, well, it's this picture here. So basically, the theorem, to be very precise, is that for smooth data, initial data, there exists some t, which is less than infinity, such that you get this final state, such that this picture holds, or the splat singularity. It doesn't really matter. So basically, what we're saying here is that you can start with something smooth, and then in finite time, you have this self-intersection that occurs. And I'll state a few corollaries of what this intersection actually means in this particular context. Does that answer your question?
But with any geometry of the initial domain?
Oh, it cannot be so simple.
No,
So
I should say there exists. Let me add this, which will clarify. Sorry, there exists smooth initial data such, and there exists this time t. So the proof is to show that you can find initial data such that this holds. The question you asked is substantially more difficult, and this is actually work in progress, which I'll discuss in a moment as well. So there are a few corollaries of this. Let me discuss them.
So was thinking of after the time of this capital T time, so the physical phenomena exist.
Yeah, physically, you can either get these jets that emanate out from the collision, or if there's surface tension, you can get these droplets that form. And there's been, for about 100 years now, there's been some pretty spectacular high-speed photography, which has captured what happens after splashing. As far as the theorem goes, the mathematics stops once the collision occurs. There's one thing I can say post-collision, but it's not very physical. So the corollaries to this are as follows. At this time of contact, so here we are at time capital T, and let's say in the splash case in a point x naught, so the vorticity becomes infinite. So you get the limit, let's say, as t approaches capital T and x approaches x naught of omega of t comma x is equal to infinity. So at that instant of time, you have this jump. You can imagine the flow going this way here and going this way here, and then as at the time of contact, the solution is well defined, but you have this infinite gradient, if you like. Two is you can now you sort of have added to the collection of well-posedness results for Euler, because you can start the problem, if you like. This is an artifact of the proof with a self-intersecting domain, as long as you pick an initial velocity field that pushes the two surfaces apart. So you have well-posedness, I'll put a little asterisk here to mean that under certain conditions of velocity for Euler with self-intersecting domains. And the third corollary of this is that you can start, it's sort of this picture, you can start with a graph, and then you can get an infinite slope, and then the wave will turn over and break. So you can go from graph to infinite slope to turn over to break. And by breaking, I mean exactly this picture here. So the crest of the wave falls and crashes onto the trough. And then I probably won't have too much time to get to this, but there's a sort of a converse result of this. So as I said, there's been some nice results on this water wave simplification where if you allow yourself to be on an infinite horizontal domain in 3 dimensions, then because of the dispersive nature of this equation, if you take very, very small initial data, so you're looking at very small amplitude perturbations of a flat ocean, you have a global existence result. So these are recent results by Saiji Wu and Germain, Mahmoudi, and Shatab. Saiji Wu also had a result a couple of years earlier, around 2009, of almost global existence in 2 space dimensions. There's a little less dispersion in 2 dimensions, so this means that if your data is size epsilon, you have an exponential in epsilon time of existence. And then recently, Pastiori and Ionescu actually proved that even in the 2-dimensional case, you have global existence. So this is sort of in this regime where you have a very small perturbation, and you want to know whether this will exist for all time. So the answer is yes. If you take a finite domain, sort of like this picture I drew here, it's a completely open question. These decay estimates that one uses for the linearized system are gone, and you need some other technology, which we don't know how to do yet. You can sort of view this as the complement to that. This is a question of what happens when you start with very large initial data and what kind of singularities can form. So as I said, in the one-phase problem, you can have this type of self-intersection occur in finite time. Remarkably, in the 2-phase problem, you cannot. So theorem 2, so there's one version of this due to Pfefferman, Ionescu, and Lee. And there's one version due to Pond and myself. And the basic idea is that a splash singularity cannot occur, at least in finite time. For the 2-phase problem. And the remark here is that in nature, obviously, you see waves breaking all the time. In a 2-phase problem, instead of thinking of vacuum or something out here, you have a fluid, and air is also being modeled as a fluid. And it's this jump in the normal component of velocity requirement for it to be continuous is what's preventing this occurring, roughly speaking. And the remark is that for a singularity to occur, you need a breakdown in regularity. So basically what has to happen is that the wave has to lose regularity. In other words, you can't have this picture that I've drawn here where the hypersurface, in other words, cannot remain locally smooth. It has to form a singularity before it can actually break.
So is this with surface tension or?
Yes.
The proof doesn't rely on surface tension so much because it's sort of you're disproving it. So, for example, our proof will also work for the 2D compressible Euler case where there's an existence theorem that Secchi and his Kuhlenbell have. But yes, you can think of the model I wrote with surface tension so that you have a well-posed problem and then you're asking, can this happen? And the answer is that it cannot. So Pfefferman, Ionescu, and Lee do a very sophisticated analysis of the integral kernel formulation of the irrotational problem. And what they show is this sort of double exponential bound from below, which means that if it happens, it can only happen in infinite time. And what Kutan and I do is we give a proof by contradiction. We actually assume that the vorticity along the interface does blow up, which gives us an ODE with a very precise blow-up rate. And then we completely characterize the geometry of the blow-up to show that it cannot occur. So I think what I'll do is talk mostly about the idea behind the splash singularity. I'll mostly draw pictures. I won't get very technical.
What happens in the physical plane? Physically, what happens when we don't get this? Is there too much fluid?
Yeah, basically, it's sort of as these surfaces want to collide, it's the presence of this fluid in here that sort of, it would sort of have to move out at almost infinite velocity in order to allow for this to happen, roughly speaking. And that's sort of the idea behind the proof by contradiction. Whereas when you have nothing inside here but vacuum, there's nothing that really prevents that from occurring.
Because there is a similar thing in the Bernoulli type free boundary problems, that in the one phase you may have kind of singularities, as that's still unknown, but you cannot exclude that. But in two phases, it's sort of that it looks impossible. I don't know if there is a proof of that.
So one comment to that regard is that for theorem 1, I should say that our proof actually holds pretty much for any hyperbolic system that has a local well-posedness result. So you can do this for compressible Euler, you can do it for MHD, pretty much for any hyperbolic system. As I'll discuss in a moment, the proof relies on being able to go backward in time. But it turns out that the proof of theorem 2, because it's sort of a proof by contradiction, we can sort of do this for any two-phase problem which has an interface moving with the fluid. So if you want to consider Muscat or problems like Muscat, this also cannot have a singularity while the interface remains smooth for the same sort of reason, that there's this fluid in here preventing it from occurring. Okay, let me erase this. So in some sense, the proof is sort of it's a technical, there's some technical stuff going on here, which I'm going to try and sweep mostly under the rug and just draw some pictures to explain the idea behind this. And it sort of works for pretty much any problem that, as I said, you're allowed to go backward in time. So the first idea is this, that let me just sort of talk about using the use of Lagrangian coordinates. So you can pretty much fix the domain to do analysis of this moving boundary problem in any way that you like, but it's very convenient to use Lagrangian coordinates. So my Lagrangian coordinate I denote by eta. So eta of x comma t is the position of particle x at time t. So the picture is that here's omega 0, here's particle x, and eta of t maps you to this moving domain omega of t, and here's eta of x comma t. That's the image of this. And what happens is you just solve a simple ODE, so my subscripts mean derivative. So eta sub t is the time derivative of eta. So you just look at the flow lines of the Eulerian velocity field for t greater than 0, and then you can just set eta to be the identity map at time t equals 0. And if you could solve for eta, you would know everything. You would not only know the velocity and the pressure, you would also know the shape of the boundary. In fact, if this is gamma 0, and this is gamma of t, then gamma of t is just eta of t acting, mapping gamma 0. In other words, it's the image of gamma, the reference boundary by eta of t. In fact, you know more than this. You in fact know how particles are moving along the boundary, so you know everything. And I'm not going to say too much about this, but I'd like to write the equation down just so you see where this is going. So on the Eulerian side, you have u and p, and on the Lagrangian side, you have what I'll call v and q. So in particular, I'm going to let v equal u composed with eta, and q equal p composed with eta. And then every time you want to differentiate u, you see that u is v composed with eta inverse. Every time you differentiate p, that's q composed with eta inverse. The derivative of eta inverse is always floating about, and I'm just going to call that A. So this is a 3 by 3 matrix. It's just the gradient of eta inverse. And then you can write this equation as, so you can write Euler as the time derivative of velocity. This now becomes the full material derivative, so the good news is you lose that vection term, but then you pay the price of a pretty weird nonlinearity. So what was a linear pressure gradient now becomes something nonlinear. But the good news is this is now on the fixed domain, omega 0. And what was a linear constraint for the divergence becomes something which is, I'll just write it using Einstein's summation convention, AJI, dVi, dxj. So again, linear divergence becomes something nonlinear, but the good news is everything's on the fixed domain. And now you have q is equal to 0, gamma of 0. And you can solve this problem as long as you can get a nice existence and uniqueness theory as long as you satisfy the Taylor sign condition. And in particular, for the purpose of the talk, I have to pick some regularity, and for no particular good reason, the norm I want to use.
Excuse me, I thought that in compressibility was the fact that the determinant of A is 1 everywhere. Is it the same as what you...
It's completely equivalent. So divergence of u equaling 0 implies that the determinant of gradient eta is identically 1. So that implies that this A is also the cofactor matrix.
So you could have written that determinant of A equals 1 instead of the second line on that question.
That's right.
So you must have a reason. You must have a reason to write it that way.
Well, not a very good reason. It's more just to make an analogy with the equation that's no longer on the board, but it's essentially to make an analogy with div u equals 0. This sort of thing is very useful when trying to do estimates because you always get derivatives on v, which because of this relation can be replaced by derivatives on eta. But no, there's no particularly good reason. You're absolutely right. I mean, this is completely equivalent. So this is what makes the incompressible problem a great deal easier than the compressible problem, in that here you have a nice constant, whereas in the compressible problem you have a wave equation for this quantity at best, and at worst a very degenerate wave equation for this quantity. But the norm for this problem, which I'm just going to call E of t, or the energy if you like, requires a fractional Sobolev norm for eta. And just for kicks, I'll use h4.5. And the velocity loses half the derivative. So this is the quantity that remains bounded for a short amount of time. And in particular, the existence theorem tells you that if you start with initial data such that at time 0 this quantity is bounded, then there exists a small, very short time capital T on which this quantity remains bounded. And this is the theorem that I'll need to use to construct solutions to this, to construct these splash singularities. So let me just outline the procedure here and what has to happen. So these are hyperbolic-like systems in the sense that they're time reversible as long as things remain sufficiently smooth. So the idea is, what the theorem is basically asking is, are there smooth initial states which in finite time have this self-intersection property? So the idea behind the proof of theorem 1 is as follows. Suppose that you could start with this state here. So there's this point x0 of singularity, and I'm going to call this domain omega s to just for s for splash. So suppose you could start with omega s and us as the initial velocity field. And suppose there was a sort of a well-posedness result for these self-intersecting domains, then this theorem would be quite easy because you would just run backward in time. So you go backward in time. And if this local well-posedness result that I stated covered a domain like this, it would tell you that there existed some time negative t. So you run backward in time, and then wherever you end up would be, so this is at time t equal capital minus t, and this is now time t equals 0. And if you could do this, you would construct your initial state, so to speak, from which you could then run forward in time and infer that you ended up at the singularity you were trying to construct to begin with. And so in some sense, the whole problem reduces to making this question rigorous of how does one construct a solution when you have this intersection. And again, I'm drawing this as a point, but it could be an entire hypersurface. And in some sense, the philosophy behind why something like this should work is that if you're swimming inside of this fluid and you're looking at the wall that's the boundary of this domain, from the inside everything looks smooth. The only thing that's bad is this cusp that forms on the outside, but that isn't seen by when you're inside of the fluid. So everything looks locally smooth, and it's just a question of how to make this rigorous. So here's the idea. So I'm just going to draw some pictures here. So the first step is to define something that I call a generalized domain. So I'm going to sort of draw this as an, I'll show you. Call this omega. So here's a generalized domain. It's intersecting at this point x naught. And what I want to do is I want to cover this with a bunch of coordinate charts. So there's going to be one distinguished one around this intersection point, which I'll call U0. And then I want to add a bunch more coordinate charts. So here's U1. Here's U2, and I want to keep going around the boundary until I get to UK and UK minus 1. So basically the idea is the following.
So I mean, this doesn't need to be specified more than geometrically. It looks like this.
Say again?
You don't need to specify it more than geometrically. It looks like this.
That's right. Except for I have to tell you what's mapping to what. I want to sort of construct local diffeomorphisms, which are standard in every chart except for the one that surrounds the singularity. So, I want to cover gamma 0, or I'll call it gamma s in this case, which is the boundary, with k plus 1 coordinate charts. So the easy ones are the green ones. That's quite standard. So for L equal 1 up to k, I choose theta L so that it maps the upper half of the unit ball, which I'll call B plus, into omega intersect UL. And it's going to flatten the boundary, so it maps, let me call this boundary B0, so it maps this flat boundary B0 to this piece here, which is gamma, I'll call this S here, gamma S intersect UL. And then it has to have a certain regularity, so this defines what it means for a domain to have a certain regularity, so I'll just say theta L is an HS diffeomorphism. So if one is following this norm, then it would be of class H4.5, which means the boundaries of class H4. And then for this one guy, for U0, that has two charts. So I'll call the intersection, so basically I'll split this. I'll assume without loss of generality that this is the axis x3 minus x0 equaling 0. So this is x3. And I'll sort of split it into this piece here, which is u0 plus, and this piece here, which is u0 minus. And then there's two charts now, so theta plus minus maps the upper half of the unit ball into u0 plus minus. And it's mapping the boundary. Each one of these guys maps b0 into u0 plus minus intersect gamma s. And each one of these guys is also HS diffeomorphism. So there's k plus 1 balls, if you will, or neighborhoods, and there's k plus 2 diffeomorphisms. And the idea is that now I can take these equations here, which I wrote on a domain, and I can localize them into each one of these, in each one of these charts, and reduce the problem via partition of unity to k plus 2 problems on this half ball B plus. And then eventually I'll patch everything back together. So this is this so-called generalized domain omega s. Okay, so that's step 1. Step 2 is I need a splash with this velocity field us, so I call this the splash velocity. And I'm just going to draw the picture as to what's happening right here. So here's u0 plus, and just to sort of make it clear, I'll move it to the right. Here's u0 minus, and here's what the splash velocity has to look like. So here's us, So what I mean by this is that forward in time, it pushes together. So push together, which means that backward in time, it spreads apart. So that's the splash velocity. And then finally, step 3 is what's called the splash pressure. So you solve minus Laplacian PS composed with theta L is equal to the trace of the gradient, it's quadratic in the splash velocity, and you solve this in each chart. So you're really solving this problem just on each little half ball. I should write with some cutoff functions and stuff, but I'm not worrying about it. And then PS equals 0 on B0, again in each chart. And then again, you have to check that you're satisfying the Taylor sign condition. This is automatically the case if you have irrotationality, and if not, you just have to make sure that you do. And for the most part, these sorts of velocity fields always kind of guarantee that anyway. So now the idea is, okay, I'm all set up. I know I've localized this problem into each chart. How do I make this definition rigorous? How do I prove that something like this is really a solution to Euler? And this takes an approximation. So the idea here is that I'm going to approximate this generalized splash domain by a sequence of smooth domains that have a little distance epsilon between where there used to be a contact, I spread them apart by a distance epsilon. And then the idea is that once I do this, I have a nice smooth domain, and I can apply the local well-posedness result, and I get a time of existence, which now depends very badly on epsilon, and then I have to prove that everything is epsilon independent, and then I can define this initial state as some sort of limiting process. So, oh, there's a box.
You don't require, I guess, that this example you start with, that's analytic, or?
No. It's of this the domain here.
Yes.
It's in this case it's HS, where I'm thinking of S as being 4.5.
So that means, okay, that means when you start with solutions, you don't get analyticity of them.
No, I don't like anything analytic, so I avoid it.
Okay.
Is it more regular than the threshold for which we have well-posedness, local well-posedness?
It's so if there's no vorticity in the problem, the best you can ask is a domain which is of class H3.5, meaning the boundaries of class H3. And if you have vorticity, you need to beat the Sobolev embedding for the time differential, the time derivative of the gradient of velocity, which is unlike in usual conservation laws where it's just the gradient of the velocities.
I mean,
But yeah, so this is actually the limit, this is the well-posedness,
there is a local existence theorem.
which is this. So I'm not above it, I'm at the local existence there. Yeah.
Sorry. For that backward in time problem, how can you see that there exists a velocity, us, such that the pressure satisfies the Taylor sign condition, Rayleigh-Taylor?
But you give it.
So as I said, if it's irrotational, it's automatic. And if it's not irrotational, then you have to check. You have to actually compute, so you have to pick so for example, if I take 2 half balls, I can get an analytic solution in which I can verify it. And so I can always pick, let's say, a small perturbation of 2 half balls.
So you verify that it is always satisfied in that case?
In the irrotational case, the trace is positive.
So the maximum
And
principle.
the maximum principle tends to.
Yeah. But even if it's not irrotational, you can check for certain geometries that you satisfy the Taylor sign condition. And then if you think of starting with geometries which are small perturbations, then you still satisfy the Taylor sign condition. And so this is possible. Okay, so now the idea is this. Now you form an approximate smooth domain. So I'll say epsilon approximate domain omega epsilon. So the idea is basically this, that you're going to look at just these two charts, and you're going to do something like this. So here's x naught. So here's how this works. In this picture here, I take a small ball of radius r. And what I do is I choose a smooth bump function. So 0 less than or equal to psi, which is something which is C infinity with compact support in this ball of radius r. So it's 1 very close to the origin, and then it quickly goes to 0. And then I define these charts as an approximation. So theta epsilon plus is theta plus epsilon psi E3, the vector up. So you see it's locally just pushing up a little distance epsilon. And then I define theta epsilon minus to be theta minus epsilon psi E3. So I'm just pushing down. And this is so what was touching at the point x naught now has this little distance epsilon, or well, at least epsilon. And now I can define this domain omega epsilon. I use all of the charts, L starting from 1 to k, all of the green charts, but these two charts right here are modified in this way, and so the domain I get no longer touches. So that's a nice domain. And then I do an approximate splash pressure, approximate splash velocity, which I call US epsilon. And this is defined as follows. You just basically say that in these two charts that are being modified, US epsilon composed with theta epsilon plus minus is the same as US composed with theta plus minus. And then for all the other charts, it's exactly the same. So basically, you just pick up those arrows and you put them now on this domain here. And then finally, you get the approximate splash pressure by solving the elliptic equation with US replaced by US epsilon. So now you're in the setting that you can apply the local well-posedness result to. So you apply theorem 0. And what you get is that there exists some time negative t epsilon and a flow eta epsilon of x comma t satisfying that the soup from 0 to minus t epsilon of this energy function, which is a ray. So let me write it again. So E epsilon of t is eta epsilon of t in H4.5. Well, let me just plus V epsilon of t in 4, H4, such that this guy is finite. So basically this means that you're starting with something that looks like here's omega epsilon, and here's US epsilon. And now you're running backward in time, and with eta epsilon of x comma t, and you end up somewhere over here with some image. I don't know, I'm not going to say too much more about it at this stage, but you get something. But everything is bad here. Everything depends sort of badly in epsilon. So now the game is to get epsilon independent estimates and define this domain here. Well, let me just begin. But by the way, what's the time? Like 5 minutes or something?
Yeah, 5 minutes.
And then it's pizza and beer?
Not immediately, we need to talk about.
Because you know, there's this very famous seminar in Spain. It's called the Pizza Seminar, and speakers can drink beer and eat pizza while giving the talk.
Yeah.
And can you write on the blackboard using a pizza?
After a few beers, that's what happens, whether you like it or not. Okay, so
And he uses beer to wash the blackboard.
So what you're saying is that you really don't start with this, with the splash, you start with something near a splash.
yeah, so what I'm gonna prove is that you can actually start from this domain.
By keeping
Via
uniform
limit.
outside.
Yeah. So what I want to show you basically, so the proof here, it's actually, you know, if you want to see very high-tech stuff, you really have to look at what Diego and his group does. It's very high-tech machinery, and this is sort of very low-tech. It's basically just calculus. There's almost, it's ridiculously simple. So, in some sense, the idea is to get, so one wants an epsilon independent time interval of existence. So you have this picture here. And here's our chart U0, and here's U0 plus, and here's U0 minus. Since I have colors, I may as well use them. Now, what I want to compare is the difference between, let me put a point y over here. And what I want to do is say, what happens, do I get lower bounds for this map eta, epsilon, when I take 2 points that are close to one another? So there's sort of two scenarios. In one case, I can put the point out here, so it's sort of outside of the two bad sets. I'll call this case 1. And the other case is I can put the point here, which is sort of kind of in the bad region, which I'll call case 2. Now, what we're using here is the fact that eta epsilon of t is, let me write it this way, of x comma t is just x plus the time integral of the velocity. So this is basically an argument using the fundamental theorem of calculus. And we can get this sort of Lipschitz lower bound. So for case 1, you look at what happens when you compare eta epsilon of xt minus eta epsilon of yt minus x minus y. And for that, there's this lower bound, which is given by some constant c1, the modulus of t, the supremum from 0 to minus t epsilon of this energy function that I erased, but that's eta epsilon in h4.5 and velocity in h4, and then the x minus y. So it's a sort of Lipschitz bound for the inverse of eta epsilon. Again, it's just coming from this this
minus-
object here,
minus x plus y on the left-hand side.
minus x
Plus
plus
y.
y. Thank you very much. And then in case 2, it's very similar. So here you are looking at this worst case scenario, and there the lower bound is epsilon plus some constant which depends on how the velocity is pushing together. Basically, this constant is saying that relatively speaking, the velocity fields are pushing this back apart backward in time, minus t squared, some polynomial of this energy function. And then there's also the a priori estimate, which I didn't write down, but it's not exactly a differential inequality, but it's very similar. It's a polynomial inequality. So what you know is that if you take the sup of this energy function, this is bounded by some number which only depends on the initial data plus time times another polynomial p2 of the sup of this energy function. And then if you put 1, 2, and 3 together, you can get, so here the crucial thing is that these constants C1, CV, the polynomial P1, P2, and the number M0, which is sort of the norm of initial data, are independent of epsilon. So 1, 2, and 3 together lead to a time of existence minus t, which only depends on these constants and is independent of epsilon. So now you have the solution a to epsilon. So a to epsilon of x comma t exists on this time interval 0 to minus t. And it's very easy then to prove, once using this a priori inequality, that once you have this time interval that is independent of epsilon, then the norms of the solutions are also independent of epsilon. The only real epsilon dependence is coming from this spreading process, and you can see that nothing bad happens as epsilon goes to 0 in each local chart. Everything remains completely bounded. So the punchline here is that how do you define the initial states? The initial in quotes. So you define the initial domain to be the limit as epsilon tends to 0 of eta epsilon at this distinguished time minus t, acting on this approximate domain omega epsilon. I.e., what I mean by this is that you can define some chart capital theta plus minus as being the limit as epsilon tends to 0 of the time derivative of a to epsilon composed with, a to epsilon composed with theta epsilon plus minus. And then this then, so what's happening here is you have this sequence of domains, and then eventually you're letting epsilon go to 0, and in the limit, so this is in the limit as epsilon tends to 0, you get this domain omega 0. And then you can prove that, you have to prove then that omega 0 is connected and that the boundary is connected. So, not a big deal. And then you can define the initial velocity field. So you can define u0 to be the limit as epsilon tends to 0 of the time derivative of a to epsilon composed with a to epsilon inverse at time minus t. And then once you have the initial states, you then run forward in time. So the construction is pretty robust, and there's essentially nothing specific to Euler that I'm using here. So if I want to do the compressible problem, that's fine. And if I want to do MHD, that's fine. If I want to do nonlinear elasticity, that's fine. But that's in the one-phase case. And in some sense, the two-phase case is really completely different because this cannot happen. So I think I've run over time, so I'll stop here. Thanks very much.
Thank you. Any questions? Remarks? There's a process, backward process in the Euler problem. So the reason I asked you about analyticity here, that they require analyticity and then they can run it backward in just very short time.
Yeah, so for parabolic problems, you can sort of, like you said, you make everything, you complexify everything. You use analytic data, you use Cauchy-Kovalevskaya, and then you have to track the strip of analyticity. And
For
make sure.
parabolic problems?
Yeah.
No, you can't.
For the one he's talking about, for Healy-Shaw, that's
Well,
what
it's
they,
not,
that's what these guys do.
For instance, you cannot apply Cauchy-Kovalevskaya to the heat equation.
no, this is.
It's not the heat equation.
It's
It's
not
it's
the
a very strict. It's a it's
I agree, but to apply Cauchy-Kovalevskaya, you need that the order of the PDE in time is equals the order of the whole PDE.
so for this Healy-Shaw / Muscat problem,
It's not
that's
a parabolic
that's what happens.
So it's not
It's not parabolic.
Well, it kind of is parabolic, but
It's
not in the
not
heat
kind of
equation
parabolic.
kind of way.
Okay.
You don't have the heat equation.
Better clarify what Healy-Shaw problem we're talking about.
Sorry?
Better clarify what Healy-Shaw problem we're talking about,
I'm thinking of, it's
Okay,
not
but
a Euler problem,
which is
which is,
not parabolic.
It actually,
it's not parabolic, no.
well, it is kind of parabolic.
Well, time dependent
so
problem.
it's not
Yeah.
the same one.
It's not the same type, but it is
It's not
kind
the
of
heat
parabolic
equation.
because there is this gain, parabolic gain of regularity that you have in Healy-Shaw,
Not, it depends which one you're talking about.
the usual Healy-Shaw.
Why, if you go
With-
if you push or if you pull.
Either way. Well, without surface tension, you have to put some, let's say you have an annulus and you put pressure equal 1 on the inner radius and pressure equals 0 on the outer radius, then you can show that that is indeed parabolic as long as it satisfies this Rayleigh-Taylor condition on the outer radius. Because there's a gain of regularity in time.
You can reverse it.
I cannot, but the guys who do the analyticity business with Cauchy-Kovalevskaya, however you pronounce it, they can and do. But that's not my game, so I only mentioned it in passing.
Anyway, so, okay. Well, thank you again.